So let's talk about how to find zeros of polynomials in general. So we have already talked about how to find zeros of second degree polynomial. So set it equals to 0 and solve for x. And then because second degree polynomial, we can just factor it and then we can solve for x. And then today we are going to talk about the rational root theorem first, and then we use this theorem to help us to find zeros of polynomials. So what is a rational root theorem? Well, if a rational number x in terms of b over c is a zero of the polynomial p of x, then p must be a factor of t and c must be a factor of s. S is the coefficient of the leading term, and then t is a constant term. Okay, so let's verify this theorem by this example here. So from earlier, we know that the actual root of this polynomial is actually -3, -1, and 2. How did we do that? Because we know that p of x can be factored into x minus 2, x plus 3, and x plus 1. So now let's say if we want to verify rational root theorem, so first of all we need to know what is s and what is t. So in this case, s is 1 because cubic is term with the highest degree here, and then the coefficient is 1, and then the constant term is -6, so t equals to -6. So if we look at the first root, -3, we can write it as -3 divided by 1. So on the top, remember b is -3, and at the bottom is c, so c equals to 1. So we can see that -3 is a factor of t, the constant term, and then c equals to 1 is a factor of s, which is 1. So same thing, we can do this for the -1 and 2. So we can see the same pattern here. But the one thing you need to notice that b is always a factor of the constant term t, and the c, which is at the bottom, is always a constant term of this s here, the leading coefficient. Okay, they cannot be swapped. Of course, we are saying that x equals to -3 equals to -3 divided by 1, but we can also say that x equals to -3 equals to 3 divided by -1, but this gives, so in this case, b will be equal to 3 and the c will be equal to -1. So although b and c are a little bit different in terms of the sign, but still b can divide the constant term, which is -6, and c can divide the leading coefficient, which in this case is 1. Okay. So now we have seen that our rules all satisfies the rational root theorem. So we can take advantage of this to use this theorem to find all possible zeros, and then we check whether these possible zeros are actual zeros or not. So how do we do this? Well, if we go back to this polynomial, if we don't know what are the roots, what are the zeros, so how do we actually find them? So the first step, identify s and t. So s is the leading coefficient and t is the constant term. And then we find all possible b values, because we want the b values divide the t, which is -6. So 6, the factor is 6, 3, 2, 1. So we have these 4 numbers, and then we put the plus and negative sign in front of them. And then the possible C values, because C must divide S, so C can only be 1 in this case. And then we put a plus and minus sign in front of it. So after we find B and C, remember all possible rational zeros are in the form of B over C, right? So what we need to do is to put B on the top and then C at the bottom, and then we can find all the possible zeros. So in this case, we have 6, 3, 2, 1, and then at the bottom is just a 1. So we have 4 of them, and then we put a plus or minus sign in front of them. So now we have actually 8 numbers. So these are the candidates for our 0 of this polynomial here. So we can see that the actual zeros, which is -3, -1, and 2, are all in these possible zeros. So the next step is to find this out from these possible candidates. How do we do that? Well, we can plug it into the original polynomial and to see whether it is equals to 0 or not. If it is equals to 0, then we say that that number is a 0. Otherwise, it is not. For example, x equals 1 is not a 0. Why is that? Because if we plug 1 into the polynomial here, and then we can see that 1 square cube plus 2 times 1 square minus 5 times 1 minus 6 equals -8 is not equal to 0. On the other hand, if we plug in that x equals to -1, and then we can see that it is actually equals to 0. So we say that -1 is a 0. And then we can do the same thing for the rest of the 6 numbers. So plus minus 2, plus minus 3, and plus minus 6. However, we can simplify our work by simplifying the polynomial. So what do we do? Well, remember, if we have 1, 0, for example, r of the polynomial, and then we can pull the x minus r out. And then the q of x will be 1 degree less than the original polynomial p of x, which is easier for us to see what are the zeros. So in this case, we have already know that x equals to -1 is a 0, so we can pull the x plus 1 out from the original p of x. And then what is qx? So we need to use long division, right? So we use the long division here to get the q of x. So q of x equals to x squared plus x minus 6, right? So we can rewrite it as x plus 1 and x squared plus x minus 6. And then we can factor x squared plus x minus 6 into x plus 3 and x minus 2. We know that we can set this equals 0, and then the 0 for the polynomial q of x is -3 and x equals 2. And then these two numbers are zeros of q of x, and so they are also the zeros of p of x. So in summary, if we are given a polynomial p of x, so how do we find zeros of this polynomial? First thing first, we need to identify what is s and what is t. And then we find all the factors of s and t separately. So what number divide s and what numbers divide t. And then we identify all possible values for b, which are factors of s, and c, which are factors of t, the constant term. And then we list all possible zeros which in the form of b over c. And then we plug the possible zeros into the polynomial to check whether the polynomial equals 0 or not. If they are equal to 0, and then this number is actually 0 of the polynomial. If it is not, and then it is not 0 of the polynomial. If it is necessary, we can simplify the problem by rewrite p of x in terms of x minus r. R is the root, or is the 0 of the polynomial px, and then times the q of x, which is a simpler polynomial.